Hi everyone, in this video we are going to talk about a really important subject, ownership. So first, stack and heap, which creates the basis for the ownership concept. Let's say you are moving to a new house and you have a few boxes of different sizes that you need to transport. The stack is like your car truck. It has limited space, but it's easy to access and you can fit smaller items that don't take up too much space. You can put the smaller boxes in the truck and easily access them when you need them. The heap is like your moving truck. It has more space and can fit larger items, but it takes longer to access and you need to plan ahead. You can put the larger boxes in the truck, but you need to remember where you put them and go back to the truck when you need them. In Rust, the stack is used to store values that have a known size at compile time, like integers or booleans, and they are stored directly in memory. The heap is used to store values that have a size that can only be determined at runtime, like strings or arrays, and they are stored indirectly by reference. So in our metaphor, you could think of the smaller boxes as values that are stored on the stack, and the larger boxes as values that are stored on the heap. So to better understand, let's start with an example. Here I'm going to create a string called s1, and we are going to say it holds the value of hello. So let's see what's happening under the hood when we create this string. So if you look at this picture here, this is our S1. So this part is stored on the stack and this part is stored on the heap. So you can think this as the heap and this is the part of the stack. So this S1 has a couple of fields that are stored on the stack. First, you can see that we have the pointer. So this field points to the place where it's stored on the heap. With this pointer, it goes to the place that it's referenced. So let's say it's going here to 0 index here, and then we can see the length is 5. So it means that go to the heap and from this point move 5 places. So 0, 1, 2, 3, 4. This is the 5th place here. And as you can see, we have H, E, L, L, O, which creates the hello. So this is the basic ideology behind strings. We have the reference on the stack and we have our string on the heap, and we are showing this reference in the stack. And that way our heap can grow or shrink, but the value that's stored in the stack is fixed. So since we know how much space this reference takes and we know how much space this length and capacity variables will have, we know the fixed size. So we are putting this on the stack for the easy and fast access, and through this we are going to the heap where it's not that organized and it's not that tidy, but using this pointer and length we can navigate in this. So maybe there are other variables in the following indexes. For them it's the same ideology. We go with this pointer where it's needed, and from there, using the length, we say if it's starting from the second index here 2, and if the length was 3, then we would say LLO. So we would have a string like this. So this is the idea, and this capacity is not our concern right now, but this length is the length of this string as bytes, and the capacity is the capacity that is given to us, so it can grow and shrink. And as we said, it's not very important in this example. So this is the way that our strings work. Now let's say let s2 equals s1. Now we create another string and we said this string is equal to that one. And let's see what's happening. So what's happening is this. We have our first string here, and we have our second string here, and we have our heap memory. So it's not copying this value here, but it's copying these directions for the string here, because it's much faster and cheaper for Rust to copy this on the stack instead of creating this big value here. So with this, we are actually having two different pointers pointing the same place, and they have the identical values here. So they are equal reference, but the value is one. It's not separate. It's not a copy of the value. It's the copy of the reference instead. So if we had a copy of value, what would we have this? So for the S1, we would have this, and for the S2, we would have this. These are separate locations in our heap. And as you can see, pointers are pointing different directions, but we have the same value. So this copy is much more expensive than the one that has happened here. So since Rust don't want to make the program slower and anything like this. It is not automatically creates a copy like this, and we are going to see how we can create a copy like this in the next lesson, but it's optional. So if you direct us to create the copy this way, we can create the copy this way, but it's not doing this automatically. So the automatic behavior you get from the Rust is not a behavior that is slow and inefficient. So this only used when needed. So let's look at this example here again and talk about the problem. So the problem here is that, as you can see, we are showing the same value with 2 pointers. So what happens under the hood is that after this block is done, then we are freeing up the space. With freeing up the space, we are actually going to this pointer and freeing up space here. So if our block ends here, and for our example, our block is this main function. When this main function ends, we want to free up the spaces. So if we look at here, we are going to go here and free up space for the S1. And then we want to do the same thing for S2. But once we go here, and we will see a space that has already been freed, and we are going to try to free up the space that's already has been freed. And this is called double free problem. To solve this, Rust works in a way like this. Once we say S2 is equal to S1, we have 2 different pointers pointing the same location here. To avoid this, after they point the same location, we are eliminating this variable. So now we only have S2, which is pointing here. And in our code, after doing this, if we say println value of S1 is, and then we are going to print out S1 here. And as you can see, we have an error. Let's check this error, and it says borrow of moved value S1. So it says that after you say S2 is equal to S1, then I created this. So we said like this is equal to this, so we are pointing the same direction. Then once this happened, it says I eliminated the S1. So this is the value that is moved to S2. After this happened, we can no longer use this. And this is called the ownership transfer. So here, S1 has the ownership of this variable here, value here. Then we are moving the ownership to S2. Now S1 doesn't have the ownership, and that's what creates the problem. So this is the basic ideology of this stack and heap. And what's called ownership is that one variable can have the ownership of a value at a time. 2 variables cannot have the same ownership of the value because of the problem we talked here for the freeing up space. And instead we are using ownership model. Either S1 can show up here, which means that S1 has the ownership, or S2 can show here, which means that S2 has the ownership. They cannot have the ownership at the same time. And here the transfer is happening there. So let's create some variables and talk about where they are stored and how it works. Here I'm going to create a variable called x, and which is equal to 5. So that's the i32 integer as we talked before. If we don't specify it, this i32 by automatically. After this created, it's stored on the stack. It's stored on the stack because we know the size of the variable, and we are putting this to the stack to fast access. Next, let's create a variable here. Our y will be string, and we are going to say this is, I say Patika here. Now this string y has the value of Patika, and we know that this is stored on the heap because this is a dynamic value. It can grow and shrink, and for that we are storing this on the heap, and we are storing the reference and necessary fields about this variable on the stack. So once we want to get the value of this variable, what we are doing, we are going to stack, and from that, with that reference, we are going to heap and we find it. So we are using the stack as the map, so that using that map we can find the variable on the heap. As you can see, this process is faster and it requires much more memory and also processor power. And now if I say let z equals to y, here what we did is now z has the ownership, and we are passing this from y to z, and we moved value here. So let's say println value of x is this, and value of z is this. I'm going to say x and z here. Now let's run this code and see what happens. First I'm going to build the project, then we are going to say cargo run here, and as you can see the value of x is 5 here as we defined, and the value of z is Patika, as we defined here on the Y, and then we move the ownership from Y to Z. Now Z has it. If we say, and the value of Y is, then we say Y here, you will see we have a problem, and it's the same problem we had before. Value borrowed here after move, which indicates that we moved the value here, but we are still trying to access it here, which creates the problem. So let's summarize what we learned in this lesson. Ownership is like being the boss of a coffee mug. Just like you can only hold one mug at a time, each value in Rust only have one owner. This helps prevent spills, drops, and other accidents that can ruin your day. But owning too many mugs can clutter up your desk, just like allocating too much memory on the heap can slow down your code. By keeping values on the stack whenever possible, Rust can avoid the hassle of constantly moving mugs around and keep your code running smoothly. One example area where this concept becomes very important is blockchain development, where you definitely don't want any spills or slowdowns. That's why ownership is crucial for efficient and reliable code. With Rust ownership system, you can be sure your code is both safe, fast, just like a perfectly brewed cup of coffee. So, whenever you are drinking coffee or writing code, remember, always be the boss of your mug's memory in our case. With this speech, I want to conclude our lesson here, and on the next one, we will see how we can deal with this ownership concept and how we can create copies whenever we want. Thank you very much, and see you on the next one.